Electrical potential is the lifeblood of your rig. As a rig electrician, you have a special understanding of electric current and how to make it work to your benefit. For this reason, the drilling crew relies on you to keep electrical controls on the drill floor operating reliably. The eddy current brake on the drawworks provides braking power to slow the traveling block and drill string, which could total more than 500,000 pounds. You want it right. Throughout this program, we'll discuss a Model 49,000 brake control unit. The theory and procedures are identical on other ELMAGCO brake systems. One major exception is the Model 6300 control system, which has little similarity to the system we'll look at here. There are 3 areas of concern for the electrician responsible for maintaining the electrical portion of the brake. This program will familiarize you with the theory of operation, routine maintenance, and troubleshooting. The complete control system consists of 4 major subsystems: power transformers, the power selector switch, a driller's control unit, and the SCR assembly. Braking action occurs when a DC voltage is applied to the coils of the brake, creating a magnetic field which opposes rotation of the brake rotor. Raising the voltage supplied to the coils increases the magnetic field, increasing the braking action. The function of the control system is to supply the variable DC voltage to the brake coils. Here's how it's done. Because they're not explosion-proof, you'll find the power transformers off the rig floor, in the doghouse, or near the fire-rig system most likely. There are 3. They're single-phase delta-connected dry-type transformers, multi-tapped to accommodate different voltages. The secondary output should be between 204 and 240 volts. This 3-phase AC output is fed to the explosion-proof control box somewhere near the brake itself. At the control box, which contains the SCR assembly, the 240-volt supply voltage is rectified and sent as a 0 to 240-volt DC potential to the brake coils. How much DC voltage is sent to the coils is determined by the gating duration of the SCRs. The SCR assembly is mounted on a plate in the control box, immersed in about 15 gallons of transformer oil for heat transfer. 240 volts AC is supplied to the driller's control. The driller's control is actually a cam-operated differential transformer. The control handle rotates the cam against a movable core in the transformer. Depending on the position of the handle and core, a secondary output of about 3 to 12 volts AC is obtained. The unloaded output would be 3 to 18 volts. This throttle signal goes back to the control box to the firing module. Here, it develops a DC control voltage for the firing circuit, which produces the pulses that gate the SCRs. In its normally off position, the driller's control sends out a 3-volt throttle signal. This produces a 7.5-volt DC control signal, which tells the firing circuit to gate each SCR late in the positive half cycle of the AC sine wave. The 3-phase AC is shown here. The shaded portion represents the output of the SCR bridge. With the driller's control off, the SCRs are theoretically gated at the end of the positive half cycle, so there's no output. As the driller's control is moved toward full on, the throttle signal increases toward a maximum of about 12 volts, causing the control voltage to drop toward a minimum of 1/2 volt. This tells the firing circuit to gate the SCRs earlier and earlier in each cycle, resulting in more DC output to the brake coils. The power selector switch places a limit on the control voltage available to the SCR bridge. When the power selector switch is in the minimum position, the lower limit of the control voltage is higher than when the power selector switch is at medium. The lower limit of the control voltage is lowest when the selector switch is at maximum. This allows the driller to set the switch at minimum for least effective braking, medium, or maximum for most effective braking. Here's the ideal setup. Rig power, 480 volts AC, is supplied to the 3 power transformers. The transformer secondaries supply 240 volts AC to the brake control box, where the potential exists across an SCR bridge. Single-phase AC is supplied to the driller's control primary windings. The power selector is at maximum. The control is in the off position, so minimum voltage, 3 volts, is supplied to the firing module. This results in a 7.5 volt DC control voltage to the firing circuit, causing it to trigger the SCRs during the negative half of the cycle, resulting in no DC output to the brake. As the driller's control is moved toward full on, the voltage to the firing circuit begins to drop. This causes the firing circuit to trigger the SCRs progressively earlier during the positive half of each cycle. So the rectified voltage increases from 0 volts DC up. At full on, the AC voltage from the driller's control is about 12. The DC control voltage is 1/2 volt, and the output voltage is 240 volts DC. In order to ensure continuous, proper operation of the brake control system, several routine checks should be made. The checks are in 2 categories: peripheral checks and control component checks. The peripheral checks include the transformer oil in the control box, the brake air gap, and a check of the cooling water. Check the transformer oil every 3 months for continuity to ground and the presence of water in the oil. Put an ohm meter across the control box case and any terminal in the junction box. If the resistance drops below 1 megohm, drain the oil. Wipe the internal components clean and fill the box with a good quality transformer oil. If the oil has been contaminated with water, you'll see pockets of water in the bottom of the control box. This too is cause to replace the oil. When checking the oil, you should also remove and clean the breather if you have one on your control box. Clean it with kerosene and dry it, or follow with an electrical cleaning solution. Check the air gap at least once a month. Cooling water should be checked weekly. Look in the manual for the specifications on your brake model. Control component checks include the DC output to the brake coils, the AC output from the driller's control, AC to the SCR assembly, visual inspection of all cables, and resistance checks. If you're preparing to work on the control system, you'll need these tools and instruments: an oscilloscope, a volt ohm meter, a phase rotation meter, a megger, and possibly a spanner wrench. The voltage and cable checks should be made weekly. Check the resistance values every 6 months. Always refer to the manual for your system for the correct specifications for all voltage and resistance readings. Most of these checks can be made at the junction box on the side of the control box. To check DC output, put the voltmeter across the large negative and positive terminals. With the driller's control full on and the power selector switch set to minimum, you should read between 75 and 90 volts DC. With the power selector at medium, you should have 140 to 160 volts DC, and at maximum, 210 to 240 volts. If you're troubleshooting, and your output voltage is okay, your problem must be in the cables to the brake, or in the brake or brake coils. If the DC output doesn't check out, the problem is somewhere in the control system. To check AC output from the driller's control, use terminals D1 and D2. The voltage should range from about 3 volts with the driller's control full off to about 12 volts full on. If this isn't the case, there's a problem in the AC supply to the control itself, or the control's interconnecting cables. The AC input to the SCR assembly appears at terminals L1, L2, and L3. Phase to phase, your reading should be 240 volts for a typical installation using a 240 volt secondary output from the power transformers. While you're making your weekly voltage check, inspect all the interconnect cables. Look for snags, cut wires, any signs of damage. You should occasionally pull the cover off the power selector and spray the switch with a lubricant, like WD-40, LPS-1, or LPS-2. This will prevent corrosion and make the switch last longer. Twice a year, you should make these routine resistance checks: the brake coils, the SCRs, power select switch, and the driller's control. When making resistance checks, don't forget to shut off power to the system. Look in the manual for your brake model specs on resistance of each coil. 12 ohms at 104 degrees Fahrenheit is the spec on this 7838 brake. You can gain access to the coil terminals by removing the cover plate on the junction box of the brake itself. This brake has 4 coils connected in parallel. In the junction box on the brake, the cables marked F1 and F2 supply 1 coil. F4 and F3 another. F5 and F6 another. And F8 and F7 supply the 4th coil. To measure the resistance across each coil, you'll have to disconnect the lead from one side of each coil. Here we'll use F1, 4, 5, and 8 as common, while we disconnect F2, 3, 6, and 7 to take our individual measurements. Some brake models have coils connected in series parallel. Be sure you test each individual coil to get accurate readings. Now we'll check the SCRs. First, disconnect the leads and measure the resistance across the positive and negative output terminals. These are the ones in the junction box on the control box. Observing proper polarity with the test probes, you should read somewhere between 1 and 8 ohms. Reverse the leads, and the reading should be in the same range. Check the gate resistance from gate to cathode of each SCR. You should read 10 to 15 ohms. Reverse the leads, and the reading should be in the same range. With the entire system hooked up, the resistance to ground from any SCR terminal should be a minimum of 700,000 ohms. You can test the power selector switch and the driller's control from the junction box. Pull the leads from P1, 2, and 3, and put the select switch in minimum. The resistance across P1 and 2 should be between 1 and 25 ohms. The reading should be similar across P1 and P3. To check the driller's control resistance, pull the primary leads from terminals L1 and L2. Resistance across the primary winding should be 2,800 to 3,200 ohms. Resistance to ground from either winding should be at least 1 megohm. D1 and D2 are the leads to the driller's controlled secondary. The resistance should be 800 to 1200 ohms. Naturally, any discrepancy in a reading will indicate an open or a short in either a cable or the component being tested. All the routine checks we've mentioned will be useful means of troubleshooting the system when there's a specific problem. For instance, if you test the AC output of the driller's control and you have no reading at the junction box, go to the control itself and test the output. This way, you'll discover or eliminate a bad cable as the problem. Using a little logic and the voltage and resistance values specified in the maintenance section of your brake control manual, you should be able to eliminate each component as the source of your trouble. Don't overlook the interconnect cables as a potential source of trouble. You can use a megger to test a cable for continuity or shorts. Be sure to disconnect all leads from a subassembly at the SCR box before megging that subassembly's cables. The megger's 500 volts can damage some components. After checking cables, perform the routine resistance checks. There are some other potential trouble areas, and here are some tests for these. If the AC supply cables from the power transformers were hooked up improperly, you may have improper phase rotation. This can cause the controls to malfunction. In fact, it may cause severe damage in the control box. For this reason, always check the AC input with a phase rotation meter after hooking up the controls. This should be done every time a land rig is moved. When connecting the phase rotation meter, just remember red, white, and blue. Connect the red lead to L1, white to L2, and blue to L3. Proper rotation will be clockwise. If the rotation is wrong, reverse any two of the leads and hope that you haven't already damaged the control circuits. If the phase rotation's okay and the driller's control output checks out, make the following tests at the junction box. Put the power selector in maximum and leave the driller's control off. The DC voltage across C and CV should be 7.5 volts. Since the control is off, you should have no potential across the DC output terminals. Now, move the driller's control to full on. This raises the throttle signal, which lowers the control voltage. So the control voltage, CV to C, should be at its lowest, 1/2 volt. And you should have maximum output to the coils, 210 to 240 volts DC. Repeat the process with the power selector switch in medium. With the control off, you should have 7.5 volt maximum control voltage, no DC output to the coils. Move the control to full on. The medium position of the power selector should limit the control voltage to a 2.2 volt minimum. The DC output voltage should be 140 to 160. With the power selector in minimum and driller's control off, you should get the same reading as in medium and maximum. With the control full on, control voltage should drop to 4.4 volts DC, while the DC output should be 75 to 90 volts. If the control voltage doesn't check out, but the driller's control output is good, you can logically suspect the firing module. The voltage across P1 and C should be minus 15 volts DC in any position of the power selector. If any subsystem except the SCR bridge doesn't check out and you've eliminated cables as a problem, replace the faulty subassembly. The power selector switch is easily replaced. To remove the driller's control, use a spanner wrench to remove the bottom plate. Then, after disconnecting the wires, the barrel can be removed and the control can be pulled from the console. If an SCR is bad, replace that individual SCR. If the DC output voltage is off, you can adjust it using the high, medium, and low pots on the firing module. The firing module is mounted on the same plate as the SCRs. Adjust the high pot first, with the power selector in maximum and the driller's control full on. Then move the selector to medium and adjust the medium pot. Then do the same with low. If the voltages can't be adjusted, replace the firing circuit. As a final check, put a scope across the DC output terminals. Be sure to set the scope on a range that can handle 240 volts. Test with the power selector in each position and the driller's control full on. You should see 6 distinct, equally spaced pulses. If there's an obvious gap, 1 or more SCRs are not firing. Here we have 2 that aren't. In a case like this, recheck each SCR with an ohm meter and recheck the firing circuit by testing the voltage across C and CV. In rare cases, you may have to disconnect the SCRs one at a time to find which are not firing. To maintain water tightness, apply a gasket seal compound before you close the cover plate. Don't use an actual gasket because they aren't explosion proof. Don't try to memorize the specs for voltage and resistance checks. You can and should always refer to the service manual when you're working on the brake. What you should get from this program is an understanding of how the system works. You should be familiar with the locations of the various components, and you should know the routine maintenance and troubleshooting procedures. What are the 4 major subsystems? This one converts the Rig 480 into 3-phase 240 volts to power the system. Power transformers. This one determines the range of braking power you want. The power selector switch. This one is operated by the driller and sends the throttle signal to the firing circuit. The driller's control. And this one rectifies the 3-phase AC and supplies a DC voltage to the brake coils according to the throttle signal it receives. The SCR assembly. How does the control system work? The power transformers supply 3-phase 240 volts to the brake control. 240 volts are supplied to the driller's control, a differential transformer that feeds 3 to 12 volts back to the control box. As the handle is moved toward full on, the voltage increases, causing the firing module to decrease the control voltage. This tells the firing circuit to gate the SCRs earlier during the positive half of each AC sine wave, increasing the rectified DC output from 0 toward 240 volts. This DC voltage goes to the brake coils, setting up the magnetic field which opposes rotation of the rotor, resulting in braking action. The power selector limits the amount of decrease in the control voltage, giving you 3 different ranges of DC output and ultimate braking power. What are the 2 categories of routine maintenance? Peripheral checks and control component checks. Peripheral checks. Check the transformer oil every 3 months for continuity to ground and for water contamination. Change the oil if it's contaminated or if the resistance to ground is low. Check the air gap once a month. It should meet the specs in the manual. Test the cooling water flow rate every week. The control component checks consist of testing input and output voltages on the various components to see that they're operating correctly. These include the DC output to the coils, the AC output from the driller's control, and AC to the SCR assembly. These tests should be made weekly. At the same time, inspect the interconnect cables. Every 6 months, go through the resistance checks listed in the manual. These include the brake coils, SCRs, power select switch, and the driller's control. And be sure to check the phase rotation on the AC to the SCR assembly anytime you've reconnected the power to the system. All these routine checks will also be your basic tools for troubleshooting when the system malfunctions. Start with the cables and check each subsystem until you find the problem area. An oscilloscope will come in handy if you suspect any SCRs are not firing. Look for missing pulses. By now, you should have a good understanding of the brake control system and how to keep it operational. Put your knowledge to good use, and your drilling crew will thank you.
Thanks for giving me a break.